Hello, this is Mrs. Doro, and we are going to talk about matter this unit. This is chapter 2 in your book. Chapter 2 starts on page 36, I think, in your book. Yes, 36 and 37. And we're going to talk about things like solids, liquids, and gases, and how things change from one thing to another. And you're going to take notes on anything that I star. So if there's a star there and or it's underlined, you're going to want to take notes on it. Okay, let's define matter. Matter is anything that has a mass, which is its resistance to change in motion, and a volume. So think about everything in the world. Think about what has mass, what weighs anything. Even air weighs something, right? Oxygen, nitrogen, any of those gases, they weigh something. And volume, that it takes up space. We know that when we go to seal a Ziploc bag, that air takes up space because you have to get all of the air out of it. So even air has a mass and a volume. Something that doesn't have mass and volume might be something like light, all right, or light waves. Any kind of thing being transmitted from the sun, whether that be, alpha, beta, gamma rays, anything like that. But everything that we're pretty much going to deal with here on Earth, if you had to point to 10 things that were matter, you could point to any 10 things you wanted to, and they would be matter. Okay, properties of matter. Physical properties can be observed or measured without changing the substance. All right, so we'll start that. Things like what color something is, or maybe how hard a tabletop is. It's a solid or a liquid. What it smells like. Anything that you can observe, and it's still the same thing. So hair, I can observe your hair color. I can observe your hair length. I could even observe, how shiny it is, but it's still a physical property of it. Chemical property is the way a substance can change or react to form something new. So it has to form something new. Flammability, explosive, anything that has to do with blowing something up or catching something on fire is going to be a chemical property. If it changes into something new, let's just say we'll use hair again for another example. If I were to cut hair, it's still hair. But if I were to burn it, it's not going to be hair anymore. You're going to have those ashes that turn into something else, and you're going to have smoke. And you wouldn't be able to pick it up and say, hey, look, this is hair. You wouldn't know what it is. It's something brand new. It's something new. It's a new chemical. Okay, our states of matter. 3 general states of matter are solid, liquid, and gas. I think you guys are pretty familiar with those. And there are 2 more uncommon states of matter: plasma, extremely high temperatures, and something they just found a year or 2 ago called Bose-Einstein, which is at extremely low temperatures. Make sure you get all 3 of those. They are underlined. Everything that's underlined needs to be copied down. Solids are tightly packed and they have a definite shape and a definite volume. If I was going to draw a solid, I would probably draw it in circles, and I would show them tightly packed, touching each other, not able to move. If you think about a solid, it doesn't move around a whole lot. Sometimes things can jiggle every once in a while, tabletops or books or things like that, but there's not a whole lot of room for movement here. So they're going to be tightly packed, and they're going to have a definite shape and a definite volume. Liquids have a little bit more room. They're going to be able to flow past each other. They have no definite shape. If you think about a liquid, it's going to take the shape of whatever container you put it into. If you take water, you are going to put it into a cup, it'll take the shape of a cup. If you put it into a pool, it'll take the shape of a pool or a bag or whatever it is. So if you notice, when I'm drawing it, they're close together, but they're not touching, and they can slip over each other, but they do have a definite volume. You can take a liquid and you can pour it into a graduated cylinder and find out how much is in there. So when we're looking at the shape of a liquid, we're looking at close but not touching, not packed, so that they have a chance to move. Gases are way spread out. They have no definite shape and no definite volume. If I were to draw a gas, I would draw them way spread out, and they'd be moving very fast. They'd be hitting each other, they'd be bouncing all over the place, and they have no definite volume. I couldn't take gases and be like, let me shove them into this graduated cylinder and see how much they were. That would not work. I wouldn't be able to measure the gases in this room unless I just measured the volume of this room. All right, and then again, no definite volume. If I open the door, they escape and come in. And so gases move all over the place, and they're very fast, and there's no definite shape or definite volume. The strength of attractive forces between molecules determines the state of matter, means that when you look at a solid, because they're close together and they're tightly packed, because they're touching each other, they have a pull on each other. And when they have a pull on each other, they're going to have that strong attractive force. They're going to be held together. They're going to be tighter packed. And if it's a weak force, they don't have very much attraction on each other because they're way away from each other and they keep bouncing all over the place. And so when you're looking at gases, they're going to have a very weak attractive force. They're not going to be tightly knit. They're not going to be able to hold a lot of heat. They're not going to be able to do a lot of things because they're moving all over the place. Versus a solid, it's going to be packed. They're going to be attracted to each other. They're stuck with each other. And so you're going to have a very attractive force there. Okay, let's practice attractive force. Think about solids being tightly packed together and how when they're touching each other, they're going to have that strong attractive force. And if you're a gas, you're going to have a weak attractive force because you're way spread out. So I'm going to draw a gas down here, way spread out from each other, versus solids are closely packed. So let's take a look. And right now in your notes, I want you to write down for these 4 examples which one you think has a stronger attractive force. Okay, so here are the answers. When we're looking at oxygen or water, oxygen's a gas, so that's going to have the least attractive force, so water being a liquid will be stronger. Aluminum, because it's a solid, versus carbon dioxide, which is a gas. Aluminum is a solid, it's going to have a stronger attractive force. Iron or apple juice, again, a solid versus a liquid. Iron is going Fe, I put Fe because that's the symbol for iron. That's going to have stronger attractive force. And then water or nail polish remover. In this case, people would think it's nail polish remover because it has a strong odor, but actually that strong odor, the way it evaporates quickly, makes it weak. Water stays around longer. They're both liquids, but whichever one is going to stay around longer and not evaporate first would be the one that is stronger actually. So water in this case has a stronger attractive force. Okay, here's density again. In order to find the density of an object, what things do you need? We know that density is mass divided by volume, and is density a physical or chemical property? I hope you would say it's physical. And why? Because when you calculate mass and volume, you're not changing anything about the thing. You're just saying this is its mass and its volume, which are both physical properties. So density is a physical property. It's basically how much space it takes up and how much matter it has, basically. Showing you how to do a density calculation. You already know how to do this. You are going to get a density take-home quiz this week, so make sure you know the equation and the triangle. Put it in your notes. Okay, here's a density problem. As we go through, we look 52 gram object. That would be the mass. I'm just going to label it right there. And a volume of 26. I'm going to label it there. So what's the density? We have our density equation, mass divided by volume. I plugged it in. I showed my math. And take a look at my answer. It has correct units. So will it sink in water or will it float? With 2 grams, we know that water's density is 1.00 grams per milliliter, so we know it's going to sink. Here's another density practice problem for you in case you didn't quite get the first time. This is using the triangle, so if you take a look, we were given density and volume. Cover up your mass, and it tells you to take density and multiply it by volume, which is what we do here, and we get a mass of 15 grams. Okay, this graph always gives kids trouble. It is a temperature versus energy graph. Temperature's over here, energy's here. So take a look, we're adding energy, it means we're adding heat. We started with ice. and we're going to heat ice until we get to 0 degrees Celsius. At 0 degrees Celsius, that's when your ice starts melting. The energy is going to break the bonds from that solid into a liquid. It's trying to separate them. So here it is as a solid, there it is as a liquid. It's trying to break them apart. So it stays at 0 for quite a while. If you notice, as it stays at 0, energy is being added, energy is being added, energy is being added here, but the temperature stays at 0 because the temperature is not increasing because all the energy is going to break up these particles. And that's the reason the energy is being added. Once all the particles are broken up, then the temperature can start going up. So right at this point, right here, it starts to go up in temperature because now it's no longer a solid anymore. It's no longer ice. So now it's ice water at this point, and then it just becomes water at this point. So we're looking at ice, ice water, and then just plain liquid all the way up to the point where it's 100 degrees, which is where it's going to turn into a gas. And again, it takes a lot of energy to make water. If you think about boiling mac and cheese on the stovetop, it takes a lot of energy to get all that water to go away, to burn that pan to where all the water evaporates. Since what's happening here, it's vaporizing it until it all turns into steam. And at this point, right here, we would have no more water left, and your temperature would start to go up one more time. This chart is also in your book, but it's reversed. I'll show it to you on the next slide. Okay, here are the two charts. The first one I showed you in the last slide, and the next one is in your book. And it's on page 49, I believe. Let me turn my page here. Yeah, page 49. And it's the same graph, only if you look, temperature is on one side, and here temperature's on the bottom. So it's the graph flipped, basically, and it's energy on the side. And what it's showing is, as you have solid ice, as you add energy, you have to take a look at temperature. Temperature stays at 0 here, and it doesn't increase. So again, it stays at 0 on this side also. So it's the same graph, only we have our axes flipped. So if you take a look here on this graph, let's make it a little bigger so it's easier to see. You have solid ice, and then at this point it says energy is absorbed. So basically energy is being added to break that ice down. So you're going to have ice water, ice water, ice water in that particular section where it's going straight up. Then you're going to have, once you hit where it's about, let's see, the energy is 10, right about here, notice how it's going up, up, up. What happens is temperature increases because now it's all water. It's all liquid water in this whole stretch, and the temperature is rising, rising, rising. So imagine yourself at the beach. You have ice, a cooler full of ice. It's going to stay ice until every single piece is broken up. Then it's going to turn into water. So if you take a look what happens to your temperature is going to stay the same until you have no more ice left. Then it's going to rise. Then you're going to get warm water all the way to the point, let's just say it's a super hot day, it starts to evaporate. All right, so we're going to start adding more energy, and there's so much heat, so much heat, so much heat that eventually it's all evaporated. Then our temperature is going to start increasing again. Okay, last slide. This talks about the kinetic molecular theory. The kinetic molecular theory, basically that's a fancy way of saying molecule motion and how molecules move. You'll find it on page 45. It's in green with arrows on the bottom of the right-hand side. But this is pretty much what it says. Particles are always in motion. So no matter if you're a solid, liquid, or gas, you're moving. Even if you're a solid, you're just moving a little bit. Increasing temperature speeds up the particles. So the warmer you heat it, the faster they're going to move. And heavier particles move slower than lighter particles if you're at the same temperature. So at the same temperature in a room where it's 80 degrees, the heavier particles move slower than the lighter particles. Okay, that's it. So make sure you bring your notes tomorrow, and I will see you later.